So we're looking at sections 10.6 through 10.8. So we're looking at condensation, boiling, melting, and freezing in this video. So condensation is the phase change from a gas to a liquid. So when you see this picture and you see these droplets form because the water vapor in the air, so H2O vapor, become cold enough because of the cold bottle to become liquid water. So I'm just going to put an L and then H2O for liquid water. Remember, if you go from a gas to a liquid, the molecules release energy. In condensation, the gas molecules have a high kinetic energy. Remember, that's energy of motion, so those molecules are moving all over the place. When they return to the liquid's average kinetic energy increases, and that liquid is going to have a higher temperature. So that energy goes into the liquid and increases the temperature. You might have heard things like, oh, well, it's hot in Death Valley, but it's a dry heat. Or it's really hot back in, say, Washington, D.C., but it's so humid, it's miserable. Well, that depends upon your humidity in the air. So notice that at 10 degrees Celsius, okay, pretty cold temperature. Remember, 0 degrees Celsius is when water freezes. If you have 100% relative humidity, you have the size of the circle represents how much water vapor the air can hold. When you double the temperature to 20 degrees, that's a little about room temperature. Notice your blue circle represents 52% humidity, but the yellow circle represents how much water vapor the air can hold. At 30 degrees, which is a warm day, notice the same amount of water vapor is just 28%, because really at 30 degrees the air can hold more water, and so the yellow circle represents how much water can really be held by the air. If you live someplace where it's humid, you might have a relative humidity that is equal to this large circle, and it might be 100%, and you'd be very hot and you would have high humidity. In a humid environment, there's less evaporation. So remember, your perspiration or your sweat, you cool off because it takes energy to go into the gaseous phase. If you're perspiring and it can't evaporate because there's too much water in the air, too much water vapor, you're not going to cool off at all. You get the fish? They're sweating too. So boiling. Remember, boiling is changing from a liquid to a gas, and it happens throughout the container. All right? Remember, evaporation just happened at the surface. In boiling, if you looked inside one of those bubbles, here's your liquid water over here, and then the molecules escape their bonds and go off into the atmosphere. In boiling, if you increase the atmospheric pressure, you're going to increase the boiling point. So you can make it boil at a temperature higher than 100 degrees Celsius. So think about the air pushing down on top of the water, making it hard for those water molecules to escape. So keeping the water molecules in there if you have a high atmospheric pressure. So you'd have to give the water molecules more energy for them to escape. If you decrease the atmospheric pressure, it decreases the boiling point. So this happens up in Truckee. In Truckee, because we live up in the mountains, we don't have as much atmospheric pressure or air pressure. So our water boils. If you think back to some of the labs where we've been boiling water, it's been like 97 degrees Celsius. And you're always taught it should be boiling at 100 degrees Celsius. But that's called 1 atmosphere of pressure. 1 atm. In Truckee, our air pressure is less than 1 atm. So our boiling point is lower because these water molecules don't have as much pressure pushing down, so they escape easily, more easily at least, into the atmosphere. So have you ever wondered why you have to cook noodles longer in Truckee? It's because your water is not as hot, so it takes longer to cook some foods. Can water boil in a vacuum? So if you have no atmospheric pressure pushing down, think that your water molecules could escape without having that much energy. So what happens if an astronaut rips his spacesuit? We'll talk about that in class. So melting and freezing. In melting and freezing, you're going from liquid to solid or solid to liquid phases. And your intermolecular bonds are broken. So that's the bonds between molecules. Bonds between molecules. So what temperature does ice melt? You know that water freezes at 0 degrees Celsius, but what temperature does ice melt at? Well, remember your diagram? If we're freezing, we're going from the liquid to the solid phase. Remember that happens at 0 degrees Celsius. If an energy is leaving the system, remember here's your heat energy increasing to the right. If you're melting, you're going from a solid to a liquid, it happens at 0 degrees Celsius as well. It's just that energy is going into the system, but the temperature stays at 0. And this is under atmospheric conditions of 1 atmosphere. So freezing, this is a lake up in Greenland. Freezing is when liquid to a solid phase change occurs, and it happens at 0 degrees Celsius. So at what temperature does seawater freeze? Well, it has salt in it, and if you put salt on our roads, it decreases the freezing point. So it depends upon the concentration of the salt in your solution or in your ocean water or on your roads. And that's it.